Okay, so one of the big concepts, and this is a concept that goes through all of the units in Science 10. It goes through all of the sciences in high school. Okay, that concept is energy. Okay, the concept, the idea of energy is crucial because without it, nothing happens. Okay, energy is critically important. Okay, and all types of science look at energy from different standpoints. Obviously, biology is most concerned with chemical energy because chemical energy is what runs living organisms. Okay, which is why Unit 2 is actually not called biology in Science 10. It's called matter and energy in living systems. Okay, in Unit 1, okay, it's what is it? Interactions of matter and energy. Okay, so it's chemistry, right? And then this one is matter and energy in technological systems. So we look more at mechanical energy in the physics unit. Okay, mechanical energy has to do with the movement of objects and systems. Okay, so we'll be looking at a lot of things to do with mechanical energy in this unit. So we start out, we talk about energy for a couple of days, and then we move in, then we take a big step backwards. Right? And we start looking at the pieces that make up energy. So we start talking about things like position, time, speed, velocity, displacement, and all these things, okay, to kind of build back up for the mathematical analysis of energy. So we talk about what energy is, what it can do, then we go to a mathematical development towards looking at how we calculate mechanical energy after that. Okay, everybody kind of follow there. Okay, so energy in mechanical systems can be described both numerically and graphically. Okay, graphically doesn't necessarily mean with a graph. It can, but it can also mean like with a picture. Okay, or a graphic, which is what we have here. Okay, this is a picture of the Inuit blanket toss. Okay, the Inuit blanket toss was actually used by the Inuit people to help them hunt. Okay? Because where the Inuit live, you can see in the picture here, it's really flat. Okay? They live in the Arctic tundra. Tundra is actually, the word tundra actually means treeless. Okay? There are no trees. It's an Arctic grassland. Okay? It is incredibly flat. There are no trees, there are no rocks, there are no mountains, there are no hills. Right? So there's really no way to get a vantage point anywhere in the tundra that will allow you to see a great distance. So if your prey, caribou or whatever, see you coming, they're just going to run away. Okay? It's really hard to sneak up on them or see them from a great distance. So the purpose of the blanket toss was to allow people to see a little bit further over the horizon by throwing them up in the air. Because again, there are no hills or trees to climb to give you that better vantage point. Okay? So the Inuit people would put the smallest person in the middle of the blanket. Everybody would grab a piece of blanket and they would just fling them up in the air, okay, as high as they could go. I'm sure that it went bad sometimes, just like, the cheerleading stuff sometimes goes bad when they throw people up into the big pyramid. Okay, but for the most part, it allowed them to see a little bit further and kind of plan a way to surround their prey, okay, such as to, kill them and have some meat.
What if that small person had really good eyesight?
Well, then they probably wouldn't use them. Then they would choose a bigger person with better eyesight. All right, so this was just a thing that they use to help them hunt. Now it's more just kind of a cultural, interesting thing that goes on. But the way that it happens is by converting different forms of energy from one form to another. Right? It starts out with a person sitting on the ground on a blanket and a bunch of people holding onto the blanket. The only way that blanket moves is if the people do what? Yeah, if the people move, if they pull on it and lift it up as hard as they can. Where do they get the energy for that from?
Muscles.
Okay, where do their muscles get the energy from? Food. Okay? You can't do anything if you don't have any chemical energy in your body. Right? So these people have consumed food, they have energy in their muscles, and their muscles can contract. When your muscles contract, you're converting chemical energy into mechanical energy. You're turning it from a chemical form into a movement form. Okay? Mechanical form of energy. Okay? That mechanical energy goes from being in the muscles to being transferred to the blanket. Okay? The blanket transfers it to the person on the blanket. And they go from having no energy at all, sitting on the ground, to suddenly having mechanical energy. Their speed increases from 0 to some number as they are thrown into the air. Okay? Now, once they leave the blanket, this person's no longer on the blanket, they're way above it. Okay? As they travel upwards, their mechanical energy changes. Okay? Not the amount of it, but the type of it. When they're moving very fast and still on the blanket, they have a lot of kinetic energy of movement. As they move higher up in the air, that kinetic energy gets lower and their potential energy gets higher. They convert into each other. At the highest point in their flight, they actually have no kinetic energy. Because when you throw something up in the air at its highest point, how fast is it moving? It's not, because it slows down, stops, and then begins to fall back down. Right? So at their highest point, all of that energy that was in the muscles of the people is now potential energy in the person. That's all well and good, except now the potential energy is going to convert back into kinetic. The people on the ground have to be ready for that. If they don't, that energy will do work on the person they threw into the air. And it'll change their shape in an undesirable way. Okay? So what happens now is that potential energy turns back into kinetic, and the people have to pull the blanket really tight to absorb the energy of the person, allow that energy to do work on them, changing the shape of their muscles, using some more energy to slow them down and bring them to a gentle stop. Okay? There are a lot of energy conversions going on there. Yeah. Okay? We don't think about it, but energy is being converted from one form to another all the time. Okay? Now, the issue with that is no energy conversion is 100% efficient. So at every conversion, every time one form is turned into another, some energy is lost. Okay? Now, when we say lost, we don't mean it's gone. Okay? It doesn't disappear. It's not destroyed. It just turns into forms that are no longer capable of doing any useful work. The most common form would be heat. Yeah. Okay? Light is another form. Sound is another. Okay? Those are all the forms of energy we typically associate with lost energy. Okay, does that sort of make sense?
Yes.
Okay.
So, like, theoretically, does the Earth only, like, contain a certain amount of energy?
The universe only contains a certain amount of energy. Yes. Okay? And that energy is going to stay constant, but it is going to turn into different forms. That's why there's lots of different theories about what eventually will happen at the end of the universe. Okay? That this whole, like, entropy of the universe is just going to get spread out over such a wide area that there'll be like the big cool, right? There's also the big crunch, okay, and that the expansion of the universe will at some point end, and it'll begin, gravity will begin to win and bring everything back down. And it's kind of like this cyclic thing where you get the big bang, and the big crunch, the big bang, and the big crunch, okay? And it just keeps happening over and over, which would require, of course, all energy to always be conserved. Okay, interesting ideas. No way to prove anything. All right, so forms of energy. Okay, when we're talking about energy here in general, okay, a definition of energy is, for any type of energy, is the ability to do work. All right, so we have a definition of energy, that is the ability to do work. All right, so the other day when it snowed really bad, and your parents woke you up and say, "Hey, go on and shovel the sidewalk. Go on and shovel the driveway." Like, I don't have any energy. I can't do that. You were lying, okay? Because you had energy. If you didn't, you'd be dead. Okay? So you obviously did have energy. You didn't want to go out there and do it. But if you actually did have no energy, you'd be absolutely right. You would be completely incapable of shoveling the driveway because that would require energy. It's work. Okay? All right, when we're doing work like shoveling the driveway, okay, what are we really doing when we shovel? Moving things. Okay, if I want to move something, what do I generally do to it? Push on it, right? I push on it or I pull on it. I exert a force. Okay? Now, when I move it, I exert a force and it moves. What do we call the space over which something moves? Distance. Okay. So, work is done when you exert a force over a distance. Work changes the energy of things. Okay? Work is a change in mechanical energy. When you do work, you've exerted a force through a distance. Yes. Yes. You can measure work in joules. Okay? Energy and work have the same units because they are each other. Okay? If I want to do work, I have to have energy because work is a change in energy. So if I lift snow off the driveway, I'm taking my energy and I'm giving it to the snow. Okay? I'm lifting it up, I'm moving it over there. Right? My shovel makes noise, that's lost energy. It's sound, it makes heat against the driveway, all that kind of stuff. It's all showing that energy is converting from one form to another. Okay, so ability to do work. Okay, so for example, the sun's energy, okay, causes snow to melt in the spring. Okay, so that's heat energy, okay, coming from the sun, light energy coming from the sun. Okay, we know that a person who's just run a marathon has used up a lot of energy. Okay, a person who runs a marathon, what are they going to eat in the days leading up to that? Well, actually not everything, and there are actually not too many proteins. A lot of carbs. Yeah, okay. Marathon runners, you run anything over 3 kilometers, and you're going to want to do what's called carbo-loading. Okay? You carbo-load because carbohydrates get turned into glycogen very easily, which gets stored in your muscles and can be very readily converted into energy for your muscles. Okay? If it isn't used, though, over the course of a few days, glycogen turns into fats. Okay? So it's all fine, it's all well and good to carbo-load, but you got to make sure you're going to use it. If you don't, you won't lose it. Okay? It'll just get stored. All right. So it's not surprising, obviously, that the development of the concept of energy went hand in hand with the development of technologies that used it. Oddly enough, we built all kinds of machines that used energy, converted energy, and did work, and we didn't understand what work and energy were. Okay? It's possible to develop technologies around something we don't understand. Okay? Humanity has done it all throughout our history. That works. I'm going to keep doing that. I don't care that I don't know why. It works. So I'm going to keep doing it. Okay? I'm going to build this thing because it does this job. I don't care how, it just does it. It's good. Okay? Don't have to understand as long as it works. Okay? And that was the idea with energy, because energy is hard to explain. I mean, we can say, well, energy is the ability to do work. That's its definition. But to actually explain energy, to prove its existence, to show what it is hard, because energy isn't matter. Matter is easy. There's a desk here. If I walk over to it and it'll be in my way, I can't occupy the same space as this desk because it's matter and I'm matter. Okay? Can I walk through energy? Absolutely. Doing it right now. That's the light. Walking through it all the time. Okay? Energy is not a material. That's what makes it difficult to explain and measure. Because it's not a material. It's not something we can hold in our hands, okay, and say, oh, I've got some of this. Okay? It's not something we can do that with. Okay? So it was difficult to describe because it involves an abstract idea and not a material object. Okay? Experimental evidence had supported the theory that heat was a form of energy and that it could be converted into other forms as long as we followed certain principles. Okay? With these scientific breakthroughs, scientists realized that other physical phenomena and science might be explained in terms of energy, and that other forms of energy might exist. Right? So we're going to look at some of the types of energy here. Okay? So first one we're going to look at is chemical energy, because that's the one that we typically run on. Right? As much as some people would like us to have a smaller carbon footprint and not use as much chemical energy. Chemical energy is what has driven humankind for basically our entire existence. Okay? We know that when you burn stuff, energy gets released. And it's easy to find stuff to burn. Okay? And that's why chemical energy is so readily available, so easy to use, okay? And why so much of our technology is based around it. Okay? So common types of chemical energy could be a propane molecule. Okay? That's what this is here. I'm going to just erase that because I've drawn some other stuff on it. Makes it look confusing. Okay, so a propane molecule is C3H8. Okay, that's propane. So that's 3 carbon molecules that are bonded together, okay, with molecular bonds, not ionic bonds, okay, and 8 hydrogen atoms. Okay, so all chemical energy works on this same principle. If I break any of these chemical bonds, the energy within that bond will be released. Okay, and it's released as heat and light and sometimes sound. Okay, things like that. So as I burn propane, I break all of these bonds. Every last one of them gets broken, because at the end of this reaction, carbon and hydrogen are not together anymore. Okay? Now, new bonds are formed, but those bonds are of lower energy. Okay? Carbon dioxide and water are far more stable than propane is. Okay? That's why propane burns and water doesn't. Everyone kind of follow me there? Okay. So, in that reaction then, we release a lot of heat energy, okay, here during the reaction part. All right with that idea? And so chemical energy comes from the breaking of bonds, okay, between atoms. Okay, so alchemists, of course, knew this. Okay, they called these things the hidden secrets, because that's how alchemists work. They had cool sounding stuff that made it sound secretive. Okay, so all matter contained hidden secrets. Okay, and that was the energy that they could release. Okay, we know that different types of things that burn release more energy than others. Right? Certain types of wood burn hotter than other types. Okay? If you throw like aspen poplar on fire, it kind of sizzles and smolders and sometimes smells bad and makes a lot of smoke. Okay? Whereas if you throw like some cedar on there, the cedar burns quick and hot. Okay? You get a much hotter fire, okay, from different kinds of wood. And that's just based on their chemical structure. Are there a lot more bonds? Are those bonds more dense? Okay? Things like that, they release more energy. If I burned the same amount of coal as I burned wood, would I get more energy out of the coal? Yes. Yes. Okay? And of course, that led to the idea that we can refine fuels. Okay? If we take certain chemicals that can burn on their own and refine them or enrich them, we can make them burn even hotter. Okay? All right, so in general then, chemical energy is the potential energy, so it's a form of potential energy, okay, stored in the chemical bonds of compounds. Okay? When you eat food, okay, it contains chemical energy that your body uses, okay, to do work in cells. Okay, this here doesn't look much like a battery, but that is the great-great-great-grandfather of the modern AAA battery. Okay, it's called the Volta pile. Okay, it's actually where batteries get their name. If you look closely on a battery, so lots of times they'll say pile alkaline battery. Okay, because they are basically the same structure. Okay, a pile battery. A battery is a bunch of cells, okay, in a pile of cells. Okay? All right. Same thing in a car battery, except that that's a wet cell, so there's actually water inside. Okay, well, not water, but acid. So what Alessandro Volta, he was an Italian scientist, did is he stacked these different pieces of metal on top of each other and put moistened paper in between them. And what he found was that he could get an electrical current to flow through because there was a potential difference in the electrons at one end of his pile than there were at the other. Okay? And so electrons would naturally flow out of the negative post, okay, or side of the pile, okay, and towards the positive post. Okay? So it would only happen for a short period of time, and then that potential difference would be gone, and there would be a balance, and then there'd be no net flow of electrons anymore. Okay? But he discovered that, sandwiching these different metals together, okay, if he did it enough or had enough of them, he'd get more and more energy to flow through it before it died. Right? Now, obviously, we've refined that process quite a bit. Okay? All of our alkaline batteries are now what we call dry cells. Okay? They wouldn't require moistened paper, okay, or anything like that. Okay? And electricity will flow, okay, from one end to the other for a fairly extended period of time. Okay? And we rely on that technology like crazy now, especially with lithium-ion batteries, because pretty much any device that you have is now running on a lithium-ion rechargeable battery. Okay? Now, with a rechargeable battery, you've got still chemical energy, but it's being turned into electrical. Yeah, so it's a form of chemical energy, but it's being essentially turned into electrical energy. And electrical energy is the energy of moving charges. Okay? Even though electrons are incredibly small, they still have mass. And when they move, they can be used to do work. So when you connect the two ends of a circuit, okay, that's connected to a battery, to something like, let's say, an electric motor, okay, the electrons will move through that motor and they will transfer some of their energy to that motor, causing it to turn. Now, that means, though, that when those electrons return to the battery, they're not as energized as they were when they left, okay? Which is why eventually the battery dies, okay? Or becomes exhausted. Now, if I want to recharge it, if it's a rechargeable type battery, then I just add energy and I actually get the electrons to, I actually restore the potential difference, okay, in that battery. Doesn't necessarily mean the electrons flow backwards, okay? It just restores the potential difference. Because eventually, as we know, all lithium-ion batteries stop working, okay? You can recharge them a certain number of cycles and then they're kind of done, okay? All right. So, electrical energy and magnetism. So, electrical energy is the work done by moving charges specifically being electrons. Why does it have to be electrons? Protons don't move, okay? Protons are in the nucleus, okay? If that was happening, if actual moving charges were protons traveling through a wire, what would happen to the wire? The wire would get bigger. Okay, because protons have a lot more mass than electrons do. If protons were moving through the wire, okay, it would get really hot because protons don't move. There'd be a lot more resistance to them than electrons. Okay, but they would add more mass. Okay, whereas electrons are so small that you don't really notice that. Okay, so the Volta pile was made of stacked layers of two different metals, okay, such as copper and silver, and moistened with paper sandwiched between each layer. If a wire connected to either end of the stack to an external circuit, the Volta pile could produce a constant electric current. Okay, so it was invented by Alessandro Volta in the early 1800s, and it constituted the first battery. It provided evidence of a connection between chemical energy and electrical energy. Okay, so a very common way, again, for us to produce electrical energy and then mechanical energy is to start with what kind? Chemical. Okay, so even if you buy an electric car, okay, you're still using chemical energy. Okay, and you're using chemical energy every time you charge it. Okay, because that's where your electricity comes from.
Electrical cars aren't actually that.
They can be.
All the heavy metals.
The car itself is, but like, where does that?
No. All the heavy metals in the batteries in the car and all that stuff makes up for the. It's like it's better for the world to get a diesel truck than to get an electrical car.
Well, that's a bit of a stretch. I like where you're going with that because I think but it'd be a bit of a stretch to say that. You're right. The process of mining lithium and the disposal of the batteries after they're exhausted is not good. Okay, if you've ever seen a lithium mine, it makes an oil sands operation look like Greenpeace. Okay, like it's awful. It's just total strip mining, leaching of metals, all kinds. It's bad. Okay, and then there's the issue of what do I do with this dead battery now? And there are companies now that are finding ways to actually rebuild and kind of recycle the lithium-ion batteries. Okay, but it's not, the technology's not really there. The other issue is, of course, that, at least in Alberta and most places in the world, if you plug in your car, you're just putting a bigger load on a coal or oil-fired electrical plant, which is going to have a large carbon footprint compared to something else. Now, that said, our electrical generation by coal and stuff is very low emission. Like we have very stringent standards on that. The benefit of an electric car is that it does convert its source energy to mechanical energy far more efficient. Okay? An internal combustion engine, especially like the bigger they get, the less efficient they become. Okay? A typical internal combustion engine will run at about 15 to 17% efficiency. Okay? That means 15% of the energy contained in the fuel actually ends up driving the car forward. In an electric car, it's closer to 95. Okay, so an electric car is far more efficient at converting its energy source to movement than is an internal combustion engine. Okay, that's where the benefit of the electric car comes in. Whether you're, if you look at in total, is the total environmental footprint of each one significantly better than the other? It's probably a toss-up, right? But in the end, you're making choices. You're trying to do what's right.
I'll take it over to my mom.
No, I totally hear what you're saying, right? Like electric cars, they rely on batteries that have lots of bad chemicals in it. But the process of refining fuel is also not good. So, I mean, it's 6 of one, half a dozen of another. You got to get to work somehow. Getting to work takes energy. You got to figure out how to do it. Okay? So if you could bike, you would certainly be reducing your carbon footprint by biking or walking. Okay? There is no doubt that biking or walking will significantly reduce your carbon footprint. Okay? Yeah. All right.
Isn't diesel fuel like the worst possible fuel cheaper?
There's a lot more
compared to gasoline or propane or anything.
Not as much anymore, especially with the new pollution stuff that goes on a diesel engine, the urea thing.
Oh, okay.
Yeah, I mean, if you have a diesel truck, you have to every once in a while get this fuel conditioner that's basically urea refilled, and every once in a while your waste gases will be cycled through this urea chamber that reduces the amount of sulfur that comes out.
Is it like a special catalytic converter?
It's a special type of catalytic converter, yeah. Okay, now, the other types. We talked about electricity. Now we want to show the relationship between electricity and magnetism. They can very easily be converted into one another because electricity can have magnetic effects and magnetism can have electrical effects, right? And that's because of the nature of magnetic fields and electrical charges, right? So, a guy named Ørsted discovered that electricity produces a field around it, and that field can have a magnetic influence. He discovered it almost by accident. He had a current-carrying wire, and he had a compass. And when he moved the compass close to the current-carrying wire, he found that the compass went from pointing toward the Earth's magnetic field source, the North Pole, okay, to parallel to the wire. Okay? Now the only thing that could cause a compass to change direction is a magnetic field. And as soon as he moved the compass away from the wire, and he didn't have to move it very far, the compass went back to pointing back to north. But as soon as he got the compass close to the wire, it would orient to the same direction the current was flowing. Okay? So what he concluded is that moving charges produce a magnetic field. This is the whole idea that those people that don't want like a cell tower near them will argue, okay, or they don't want big power lines going near their house because they think it causes brain tumors, okay? Because they'll tell you, and there is some truth to this, that electricity has magnetic effects. That's electromagnetism, or even in some cases, electromagnetic radiation. Okay? And so there's a fear around this. Now, the thing people don't know is that the strength of the field decreases exponentially with distance. Okay? That means if I'm standing right next to the field at a distance of 0, I'm at its most intense. Okay? If I walk 1 meter away from it, the field will be considerably smaller. If I double that distance to 2 meters, I now have 1/4 of the intensity of the field as I had when I was standing 1 meter away. If I double my distance, I decrease the effect by 4. Triple my distance by 9. Okay, it's exponentially related. So you don't have to get very far away from a current-carrying wire before its magnetic effects are virtually gone.
So how does a microwave work?
By producing an incredibly intense set of infrared waves. So there's a magnetic field, an electric field, magnetic field produced by the microwave. Okay, and it produces infrared waves that cook your food. Okay, if you have old Wi-Fi, firing up the microwave will just kill the Wi-Fi.
So if you walk by a microwave and your phone's on your Wi-Fi, kind of.
If you have older Wi-Fi, yes. Newer Wi-Fi, like 5G stuff, is not affected by it. Okay, but yes, the older Wi-Fi, I remember that happened to me one time because I was watching the NCAA basketball tournament the first weekend when there was like 20 games on at one time, and I had TV on, I had my iPad on, I had this little location-free TV, I had my laptop, and my phone. And I was, why? Because it was crunch time in like 5 big games, and I had my bracket, I'm not sure I was going to win. And all of a sudden, my kid comes over and throws something in the microwave, and they all go out like, ah! Because it was like, overtime in one game, there's like 5 seconds left in another, and then all of a sudden the Wi-Fi goes out because the kid throws something in the microwave and goes, turn it off! But yeah, okay, so yeah, it produces these magnetic effects, this electromagnetic radiation that interferes with your Wi-Fi signal. Yes. Okay, so Ørsted essentially figured out that yes, if I produce a strong enough electrical current, I can produce a magnetic field. This is what led to essentially like the first radio transmitter. This was kind of the birth of that idea. Okay, strong enough electrical currents and electrical fields produce magnetic effects that can be used to transmit information. Okay? It was kind of a big deal. It also kind of led to the idea that you could produce an electromagnet. That's an idea. Now, another guy named Faraday, he discovered that the opposite is also true. A magnet can produce an electrical effect. Okay? If I have a coil of wire and I push a magnet through it, the magnetic field around the magnet will push the electrons through the wire. Okay? They'll try and move away from the magnet. Okay? And moving away from the magnet means that they flow through the wire and you get an electrical current. Okay? As the magnet moves through the wire. Right? So Faraday actually was responsible for kind of developing the idea behind the first generator. Okay? A generator, okay, that produces alternating current basically just has a magnet going back and forth between inside a coil of wire. Okay? That's why it's constantly producing an alternating current. Current goes that way, it goes this way. It goes this way as the magnet goes back and forth. Sort of make sense? All right, so Hans Ørsted discovered that an electric current in a wire could produce magnetic effects. Okay, Michael Faraday, okay, found that if you moved a magnet through a coil of wire, that you could cause an electric current to flow through the wire. Okay, so they found kind of the opposite thing, but they found certainly that there is a very close relationship between magnetism and electricity. All right, then we got Seebeck. Okay, so he was a German, Estonian and German scientist or physicist. Okay, and he'd seen all this stuff that had been done with magnetism and electricity, and he thought there's got to be a way to turn heat into electricity because everything produces heat. Okay, all energy conversions end up producing heat as a waste product. There's got to be a way to turn heat into something useful. Maybe I can find a way to turn heat into electricity. So he went back to this idea, kind of some of Volta's idea, okay, with differing metals producing a potential difference. Okay, he also knew that when something got hot, the particles in it would move fast, but the things heated up at different rates. Okay, so he thought if I could get the particles in different metals to move at different rates, then I might be able to get their electrons to flow in unison in one direction, creating an electrical current. Okay, so what he did is he took Ørsted's experiment to test this. He put a compass needle in an apparatus that looked like this. So he had a copper block, well not a block, but like a copper bar, okay, placed on top of an iron bar. Okay, those two things heat up at different rates. What he did is he applied a heat source to the iron bar. The iron bar started to get hot and its particles started to move. They transferred their thermal energy, their heat, to the copper, and it started to move. Okay, its particles started to move back and forth. But copper conducts electricity or allows electrons to move far more easily than does iron. Okay, so what ended up happening was he got a very weak electrical current flowing through the copper wire, and his compass needle turned to orient parallel to the copper. Okay, so he discovered you can turn heat into electricity, but the conversion isn't very good. It's incredibly inefficient. Right? It's not something we would use to generate large amounts of electricity. Okay? But he had invented what is essentially the first thermoelectric converter, or thermocouple.
How efficient?
It's not very.
Like what's the biggest thing you could run with it? Like if you boiled a pot of water and you just boil it and stuff.
Oh, that'd be like, you would never use a thermocouple to do that. The heat directly to the water would be faster. Right? Typically what a thermocouple is used for is like a circuit breaker. Okay? We know that if too much electricity goes through a circuit, the circuit starts to get hot. Right? That's what can start electrical fires in houses, which is why we have breaker panels in our houses. So as the wires get hotter, enough energy is generated inside this thermocouple that a little tiny switch will be popped. Okay? That's your circuit breaker popping. Okay? Now the current can't flow through because the circuit's open, and your house doesn't burn down because the circuit doesn't overheat. Okay? That sort of makes sense? So a thermocouple can be used in a circuit breaker. It's also used in certain models of electric and hybrid cars. Okay, so your high-end cars like a Tesla, things like that, Honda uses this in their hybrid and electric cars as well. In the brake rotors, they build in thermocouples. Okay, now when you apply your brakes, do they get hot?
Yes.
Absolutely, they get really hot. In fact, a lot of heat is generated by using your brakes. So what they've done, what car makers have done, is they've just embedded thermocouples into the brake rotor, so that when you apply the brakes, the heat produced can generate a small amount of electricity, which can go back and charge the battery. Okay? It basically just means all that kinetic energy, all that stuff, all that energy that was used to get you up to speed, not all of it gets wasted when you stomp on the brakes. Okay? Now, the thing with having thermocouples in brakes means that if you're slowing down more gradually, they work better. If you just stomp on the brakes, you don't get a lot of that energy back, okay? Because they kind of lock up. Okay? Even if you have anti-lock brakes, they're still going to lock a little bit. They're not going to work as well as if you slowly decelerate. Then they generate that heat more evenly, and the thermocouple can work better.
Could you take your wheel, because your wheel turns, so you the axle, like a second axle on it, that connects to a magnet, so then the magnet turns, and then the magnet creates an electric force to charge your battery.
Okay, I see where you're going with that. The problem is that you have to have a magnetic force that was opposing in order to get that input of energy, which means you're trying to drive the wheel to drive the car forward, but you're trying to take energy away at the same time. Yeah? So I see but you're trying to get something for nothing with a system like that. It's like a perpetual motion kind of thing. And so it wouldn't work. Like you already have a device in your car that is, if you have an internal combustion engine that's charging your battery, your alternator, it's making electricity, right? So it's just a little generator that runs off a belt. Yeah, if it's broken, it squeals like crazy. Okay, all right, so Seebeck invented that first thermocouple, discovered there is a relationship between heat and electricity, and you can use one to produce the other. Obviously, we know electricity can produce heat, but it's nice to know that the other way is also true. Okay, now, nuclear and solar energy. Now, for a long time, people looked at the sun and went, man, that's bright. That was supposed to be fun. Okay, they looked at the sun and they said, that thing's really hot, warm. It looks like a big fire. It is. It's a big fire in space. People didn't understand what kind of fire the sun is, because they understood one kind of fire, chemical fire. And that's the kind we have. Okay? The sun does not run on chemical energy. It is not a chemical fire. It's a nuclear fire. It's a very different kind of fire. Okay? If the sun, was actually running on chemical energy, I think they say it in here, it would run out after 5,000 years. Okay? The entire mass of the sun, if it was made of chemical energy, would be exhausted in 5,000 years. Thankfully, that's not the case. Okay? Thankfully, the sun runs on nuclear fusion. Okay? Now, there's two kinds of nuclear energy: nuclear fusion and nuclear fission. Okay? And we talked about those back in the chemistry unit. One involves forcing atoms together. One involves splitting single atoms apart. Right, so the sun runs on this nuclear fusion idea. The gravity of the sun, because the sun's mass is so big, to give you an idea, that's the mass of the sun. Okay? 1.99 times 10 to the 30 kilograms. To give you a comparison, this is the mass of the Earth. It is hundreds of millions of times smaller. Okay? Like if you look at all the mass in the solar system, 99% of it is the sun. Okay, so that includes all the big planets. Okay, the sun is massive. Right? Because of all this mass, the sun also makes a lot of gravity. Its gravitational pull is so strong that it can push hydrogen atoms together, force them together, fuse them together. Okay, and when that fusion happens, energy is released. Okay, so the sun didn't always burn like it does now. Okay, when our solar system, like 10 billion years ago, was just in its infancy, there was a cloud of gas near the center that was collecting. Okay, eventually that cloud of gas became heavy and dense enough that nuclear fusion began, and that was the birth of the sun. Okay, that doesn't happen anywhere else. Okay, nowhere else in the solar system is there enough mass to cause a hydrogen-hydrogen fusion reaction.
Do you think Earth already developed like solar farms in space, or do you plan on the sun and
it's possible. The problem is transmitting the energy back to Earth.
So it would be like a really crappy conversion for like energy.
We just don't really have the technology for it yet. There's ideas out there, like Nikola Tesla had all that wireless transmission of electricity ideas, but we haven't been able to make it work.
So Elon Musk wanted to nuke both sides of I forget. I think it was Mars or something, but he wanted to heat it up. How does that work?
It doesn't. Elon Musk has lots of really cool ideas. He's by every stretch of the imagination a visionary, but sometimes visionaries come up with really bad ideas. Like
Why do you
nuking
think that?
places.
He made like solar panel windows or something, so like your windows like
Yeah,
solar.
that's a great idea.
It's pretty cool.
Yeah,
Why do you think that would work?
I don't. The idea has been there for a long time that part of terraforming Mars would involve having to get it warmer and release lots of the water vapor that's present in its in carbon dioxide that's present in its polar caps. Nuking the caps would release a lot of that. But same idea is that if we nuked Venus enough, we could blow the cloud cover off and make it habitable. But you have to nuke it a lot. There's kind of some side effects to the nuking process.
There's radiation in there.
No, it's all well and good as long as you don't mind, your children having 5 arms. Okay, so nuclear energy, guys, is potential energy, okay? Nuclear energy is potential energy, and it's potential energy stored in the nucleus of an atom. When you alter the nucleus of an atom, that potential energy gets released, usually in the form of electromagnetic radiation. That's light, heat, X-rays, gamma rays, and all the other bad ones that come along with that. Okay, how many people have seen that thing before? Yeah, Newton's cradle. Okay, that's called Newton's cradle. That got Newton in a lot of trouble. Like, it nearly got him beheaded. Because people thought he was a witch. And he lived back in the time when that was bad. Okay? So, he builds this thing, pulls the one ball away, lets it go, and it goes back and forth. Okay? And immediately he's trying to figure out why that happens. He knows he's not a witch. He knows there's no magic to it. Okay? He just lifted up the ball. When he lifted up the ball, okay, he did something to it. He gave it, and this is what he was trying to explain and what got him in trouble. He gave it a piece of himself. Because that's what he was trying to explain. Because you have to remember, the time in which Newton lived, people were not as educated as they are now. So he was trying to figure out a way to explain why that ball would cause the ball on the other side to fly up in the air. Okay? And again, you got to remember that when Newton was around, this idea of energy was not fully developed and not fully understood. Okay? So he said, I gave it a bit of myself, and when I let it go, it took that bit of myself and transferred it to the other balls that were hanging there, and then when it got to the other side, there was nothing to stop that last ball from taking that piece of myself and flying away from the other balls. Okay? And then it would come back down, and that little piece of myself, okay, kept the object moving back and forth. People looked at him and went, you're a witch. You gave that a piece of yourself. He goes, well, you do it. No, I'm not a witch. I'm not touching that thing. I don't want to get my head cut off, burned at the stake, or pulled apart by horses, or whatever. Okay? Like, they did all kinds of awful things to people they thought were witches. Okay? They're like, I'm not touching that thing. You gave it a piece of yourself already. Okay? That's your problem. You deal with it. But what he couldn't really explain, because again, that idea of energy wasn't really developed yet, was that what he had done was work. He exerted a force on that first ball over a distance, giving it energy. What kind of energy? Potential energy. When he let it go, the potential energy turned into kinetic. That kinetic energy hit the next ball, transferred the energy through all of them to the last one, and turned it from kinetic into potential, and just kept swinging back, just like a pendulum swings back and forth. Okay? Really, all this was a pendulum, but the pendulum was transferring energy through some intermediates. But yeah, it got him in a lot of trouble. Okay? About 20 years after, a guy named Gottfried Leibniz, okay, another German guy. Germans had lots to do with energy in the early days. Okay? They reasoned that whatever caused the ball to move resembled a force that seem to be transmitted through the balls. Again, remember, we don't have energy here as a concept yet. Okay? He called this physical quantity vis viva, living force. Okay? Force of life, something like that. Again, kind of what got me in trouble. Okay? Latin word meaning living force. Okay? The term energy wasn't used until the 1850s, but for simplicity, energy is used here instead of vis viva. He also reasoned there were two types of this. Okay? And he came up with this idea of kinetic and potential energy. So Gottfried Leibniz was really important in developing the idea behind gravitational potential energy and kinetic energy. Okay? He also figured out that it's possible for an object to have both. And the sum of those two kinds is mechanical energy. Right? So that ball, when it's at its highest point, has mechanical energy. All of it is potential. As that ball falls, some of the potential becomes kinetic. The amount of mechanical energy it has remains the same. Just how much of it is potential and how much of it is kinetic changes. Okay? But that mechanical energy remains the same or is conserved all the way through. Okay? So, pretty important. Yeah. Again, he didn't come up with the idea of energy. He just realized that this living force came in different kinds. The living force of movement and the living force of position. Okay, that's gravitational potential. Okay, so anything that is moving has kinetic energy. Anything that can fall has potential energy. Anything that has kinetic energy has mechanical energy. Anything that has potential energy has mechanical energy. Okay? Because kinetic and potential are what make up mechanical energy. And it's possible for something to have both at the same time. Okay? An airplane flying through the air has both potential and kinetic energy. Okay? Questions on Leibniz? Okay. Okay. Now, heat and energy. Okay? Now, the ancient Greeks, obviously they had no knowledge of energy, but they speculated about what heat from fire actually was. It was something that came out of the fuel that they were burning. They had at least a rudimentary understanding of that relationship. Okay? By 1750, a guy named Joseph Black observed, and this isn't rocket science, that if you placed a cup of hot water, okay, or placed a cold object in a cup of hot water, that the cold object got warmer. Everybody knew that, but he started kind of quantifying why this is. And again, this is an experiment or an idea that led to the development of the idea of energy. There was this living force that Leibniz and Newton had an idea of, okay? But Black showed that this living force could flow. It could flow from a hot object to a cold object, but not the other way. You can't transfer coldness. You can only transfer heat. Okay? Because if you're cold, it's because you have a lack of energy. If you're hot, it's because you have a lot of it. Energy always flows from high to low, or hot to cold, in the same way that stuff transports by diffusion. But the same thing, from high to low. Everything moves in nature from high to low. Okay? So he suggested that this vis viva was this caloric fluid. Okay? Now, the fluid idea works really well when you're talking about the flow of energy from place to place. It really breaks down quickly when you realize that a fluid has to have mass. And energy isn't a material. It's also then not a fluid. It can behave like one because it can flow from one place to another. Okay? So he had this caloric fluid, and based on this idea of caloric fluid, he developed the science of thermodynamics. That is how heat moves from one place to another and can be converted from one form to another. Okay? So even though he was wrong about it being a physical fluid, he developed and observed the way energy moves and flows, and those were all important discoveries. Okay? So Joseph Black, okay, became the guy who came up with the principles of thermodynamics. The first law of thermodynamics says that energy can't be created or destroyed. The second law of thermodynamics says energy flows from hot to cold. Okay? Those are the laws of thermodynamics. Okay? So, while Black was trying to perfect his caloric theory, other scientists were reviving the theory that atomic motion explained heat. Okay, they suggested the movement of atoms within a substance determines its energy, its thermal energy. Okay, atoms move or vibrate more quickly in hot than in cold, and that's why heat could be transferred from a hot object to a cold object. Okay, what they did agree on is they were going to call the transfer of thermal energy heat. Okay, so heat actually isn't a form of energy. Thermal energy is what we generally call heat. Heat is the transfer of that thermal energy. Okay? So when we say, I feel heat coming off of this thing, we're both right and wrong about that. Okay? Heat is the transfer of thermal energy from that hot object to you. Okay? So you do sort of feel heat, but it's really thermal energy being transferred from the hot object to you. Okay? All right, so make sure you have that. Heat is a transfer of thermal energy. Okay, that's the definition of heat. Okay, in the same way that the ability to do work is the definition of energy. Okay, transfer of thermal energy is the definition. All right, now the relationship between heat and mechanical energy. Okay, this is an important one because this is kind of what all of our technology is kind of based on. Okay, so a guy named Benjamin Thompson. Well, he was born Benjamin Thompson. He later took the name Count Rumford because he became the Minister of War in Bavaria. His job was to supervise the production of cannons. Okay? Now, the production of cannons basically involves using a hand-operated drill, almost like an auger, okay, if you've ever drilled a post hole, okay, with a post hole auger, okay, to bore out a big lump of metal, okay, to make a nice cylindrical tube in which the cannonball can be placed in the powder and everything else. Okay, so he was supervising the production of these cannons. Well, what he discovered was that his workers, as they turned the cannons, they were putting tea kettles on top of them. And as they bored these things out, okay, they just keep turning these drills for hours and hours and hours. But they would get the tea kettles on the top of the cannons to boil water. Okay? And the only place where that energy could come from could be the drilling, which was getting its energy from the workers. Okay? So he discovered that mechanical energy, that's the movement of the drill, was producing heat energy, or thermal energy. Not heat energy, thermal energy. Okay? And that thermal energy could boil water in a kettle on the top of the cannon. So they invented the coffee break. Right? If you worked long enough, you boiled the water, you could make coffee or tea, and you could have a break. The invention of the coffee break. Okay?
So you work until...
Yeah, so you work until the tea boiled, and then, okay, well, it's time to have tea. Okay? Yeah. All right? So you could boil a kettle of water on top of the cannon while people were working. Okay? So he suggested that heat could be manufactured by the motion of the workers, first to realize heat and mechanical energy were related. Okay? Then later on, Young discovered it could go the other way. Heat could be used to make mechanical energy. It's not very efficient, okay? But it is in fact what we use in all internal combustion engines. We detonate fuel. The fuel makes heat, which causes gases to expand. That pushes the piston down, creating mechanical energy. Okay? So we use heat to make mechanical energy. All right. Talk some more about that on